This is our group presentation on particle systems. We will begin on its theoretical aspects. So, what is a particle system exactly? It is basically an array of objects that are substantial in number but not very much in size in most cases. They collectively contribute to create a large effect in an area or on an object, controlled by various parameters that would describe their overall effect. This is a general rule, however, and there may be some edge cases where some of these qualities do not align. Now, let's take a look at the example that we will be using throughout this presentation. In the game Returnal, the game requires many high-definition visual objects. These objects must be able to interact with miscellaneous objects like bullets, players, and wind. However, it can take up a lot of CPU and GPU processing cycles if they have it as individual game objects. Here, we have an image from a gameplay footage depicting a scene in the game. In the image, the player is surrounded by thousands of instances of tall grass, all with varying shapes and textures. On the enemy, there are also tentacles that come out of it that move and are animated as part of the monster. Here we have a clip of combat against a monster with a similar effect on it. The tentacles on the monster visibly fail and swirl in the air as its natural behavior. The grass reacts to the player moving through it accordingly as well, moving aside as the player passes through. Looking at samples of the game itself, if one were to create a game like Returnal, with its immersive mob and environment behaviors, there are a few problems that developers would face at all scales. They are all simple problems that can make or break the game's immersiveness into its own world. There are questions like how to make elements of the environment itself interactable, and how to animate part of or the whole monster as seen before to make it look and feel real. Here, we will be delving specifically into generating and simulating grass. You may think, why not generate each blade of grass as individual game objects and simulate them separately? In that case, trying to do so for each blade of grass will take up a lot of resources in memory and processing cycles. Therefore, with the behavior and properties of each stalk being generally the same, we can find some way to generalize how they behave as a collective type of object and allow circumstance to vary how they behave. Returnal's detailed world can face a decrease in frame rates of 20 FPS and memory leakage issues if it must calculate and play animations for every single miscellaneous game object in the world, like grass, monster tentacles, and debris. Therefore, we find ourselves asking, in this case, how would grass be simulated with a particle system? In a particle system, its properties are separated into two distinct types. One is for each individual particle, the other is for the particle system as a whole. For the properties of a particle, you can think of variables such as its spawning position, texture, and decay time, while for the properties of the system, it would be things like the duration that the system runs for or the spawn rate of particles themselves. For the properties of particles, most of the values can be generated at random. The inverse is true for the values of the properties of the particle system that generate them. For predetermined values, they can be set to a fixed number or be linked to some other value attached to the game's various other elements, such as the player. In the case of generating grass, little of its values are generated at random, save for the texture of each individual blade and where exactly it spawns. As you can see by how the properties could be configured, most values relating to movement would be set to 0, and gravity to be set to its normal value at say 10 units per second. The grass isn't going to be moving away from where it is attached to the ground, and will only disappear once the player is out of range. The variance in the grass texture will not only affect its looks, but will also vary its height. The spawning conditions are also set at specified values, giving the effects some consistency in how it looks overall. In addition, there will be some physics applied to the object to make it behave like grass and react to its environment. For other effects, the values may be different from those that are set here. For example, a smoke particle being simulated from a car performing a burnout will have textures that look different, perhaps with parts that are transparent. Its gravity will account for its buoyancy, causing it to float upwards as well. In addition, each particle will have a starting velocity and direction. In a particle system, collision can apply depending on what is simulated. For effects, collisions would not generally apply, as the object that it is simulating will generally have little to no reaction to the environment. Think something like smoke or particle effects. There are others that can be affected by collision. Things that are projectiles or are tangible effects from an attack, such as a bullet or a trail of fire, can have collision to detect what it collides with and deal damage accordingly. Collision can also apply to particles part of a system that simulates a certain terrain, for example, grass. In a particle system, velocity is a very important component of simulating its overall behavior. It is the most visible impact the environment can have on each particle. The vector that determines the particle's trajectory takes gravity, buoyancy, and any interaction the particle may have into account. The movement and transformation of each particle depends on its velocity to determine its position on the next frame. For simulating grass, it is not a necessary part of the system. However, in simulating falling leaves, for instance, it is crucial to adjust it right and make it look and feel like an actual leaf or flower fluttering through the air and onto the ground with a significant amount of air resistance. Now, we move on to implementing the ideas and elements of particle systems in Unity. I will now be passing the time to Thom.
Thank you, Kesmond. Now I'll be going through my section, Unity's implementation. So, how do we make sure that our games in Unity is able to render tons of game objects without causing too much overhead on the performance of the game itself? So, one of the solutions is through using Unity's powerful VFX graph. Funny thing enough is that it's not the same as the built-in particle system that Unity has. So, why do we not use the built-in particle system as compared to using the VFX graph? Well, that is because the built-in particle system does not have a lot of flexibility when it comes to rendering the particles we want. VFX graph allows us to create our own unique particles with different interactions, as well as being able to render 100 times more compared to the built-in particle system. This allows us to make a lot of different stuff like foliage, or such as grass, or even destructible objects like debris. Though the downside to using VFX graph is that you must use visual scripting to make your particles, which can be quite a hassle if this is your first time doing it. From my experience, it's not fun to rely on nodes to make your logic, as it can make your code hard to read or quite hard to understand. Another problem would be that you must remember a lot of behaviors for the particles in order to code out the behavior. So do take a note of that if you plan to use VFX graph for your games. Before any implementations, I want to give a few mentions to other solutions you might want to explore. Firstly is the terrain component that Unity's offer. That's the most easiest way to start when making terrains from scratch with little to no programming needed. You can get away with making highly detailed worlds and some form of interactivity if you choose this option, but when it comes to scalability and customization, it might not be the best option you might have. The harder way is through making your own particle system. It's the best way if you want to maximize your performance of your game, as you have direct control over things you can render. It's the most customizable, as you can call out any behavior you want as long as you have the skill. You can also do something cool as what Acerula did for his own rendering of his own grass. The only downside to this is the learning curve, as it requires a comprehensive knowledge of compute shaders and modern day optimizations. Now, I'll be showing you how you can make use of particle systems in your game. In this example, I'll be showing you how you can implement grass to give you the feel of how powerful the particle system is. So first, how do we even render a single strand of grass? Well, even though we must work with individual particles, we can actually group them up together through what is known as a particle strip. By doing this, we can actually simplify the process of making the grass strand by putting them together under a single quad. This will make it easier to show the particles as a whole instead of individual particles, which can be quite cool, as you can see from the diagram below. Before we improve the appearance of our grass, what are some ways to format the grass that we have now? So let's start off simple by rendering all our grass under a single rectangle. So how I did it is by setting each particles to be at a random position given a box called a AA box. This allows the particles to be spawned at any random position given a box size. As you can see from this GIF, you could see that the box can be resized in the scene, and you could see how useful it is when it comes to development. By doing this, I'm able to create random patches of grass as the game starts every single time. Afterwards, we can spawn individual grass strands using something known as a GPU event. So after we make sure the particles are spawned at a rectangular area, we go ask each individual particles to spawn individual strands of grass strands. So afterwards, the end result is what you can see here at the image below. But what if we want to take it up a notch? We can use polynoise to simulate actual terrain into our grass patch. We're going to do anything drastic to the original code. However, we can offset this value using polynoise. So the noise that we found for the individual coordinates will be used to find the height of said particles, as you can see from the image below. So using these values, we can offset the particles so that it can spawn at different heights. And now using the GPU event, we can spawn this grass strand. As you can see here, you can see how the grass are now offset at different heights because of polynoise. Now let's do something more advanced by baking the grass under real terrain. It requires more complex methods to do that. Since the particles need to know where the terrain is, we can use something called a depth buffer collision to allow particles to know where the particles should spawn. To do this, we will require a camera to help the particles to know when it hits the surface, and when it touches the surface, the camera can tell and it will notify the particles to start spawning the grass strand through the GPU event. You can see that this effect right here, where the particles immediately spawn right after it hits the surface, generating grass on any terrain that we like. So some improvements to be made on the grass. Firstly, I must make sure that the grass look like grass. In many of the grass you see in the real world, you can see how it will be sharper at the top, but thicker as it goes down. That is easily done in VFX graph, where I'm able to adjust the size of the mesh as it goes up in the height. Next is the color. What I did is that I make a simple coloring of the grass, where I use 2 shades of green to make the colors. I'll interpolate the colors from darker to lighter green as the height goes up, so as to emulate how real grass is. You could add more details here, like randomizing the shape of it and stuff, but I'll keep it simple for now. Afterwards, I add a normal banding to the mesh to make the grass fuller. This is a very cheap way to make the grass look more 3D, and it's being used in AAA titles like Ghost of Tsushima. Finally, I decided to add some finishing touches by adding a custom physics behavior to the grass. So in the example, I decided to add a random noise map to tell where the grass will move. I also added some collisions to the grass. This is done by using the collision behavior that Unity VFX graph provides. As you can see here from the GIF, you can see how the grass bends away from the player, which is expected when you play certain games. So setting up this kind of interactable particle collision is pretty straightforward in VFX graph. Hello, so this is my implementation. So over here you see the patch of grass generated based off terrain that I created it. So as you can see here, the grass is able to avoid collision with the player as well as sway based off the wind. So as you can see here, it's running about 47 FPS for 10,000 grass. Next I'll be talking about how I implemented the grass patches over here. So over here I had to make sure that the particles are spawned at a single time. So this is set to single burst to allow the particles to spawn once. So afterwards I make sure that I spawn a bunch of particles in a given location. So over here it's going to randomly spawn at any given position in this box area or a rectangle area which I set it to. And afterwards I make sure that it drops all the way down to the terrain, and if it does hit a position in the terrain, then it will start spawning the particles. So over here, here's how I set up the collision, where I make sure that it looks at the depth buffer and check whether there's a surface, and if it does, then it will kill off the particles and trigger the event for the spawning of the grass. Just a side note, this is just one of the ways that I make the grass. There's also another way where I generate the grass patches using a Perlin noise. So after the particles get killed off and it sends the event to start creating the grass, what it does is that it's going to inherit the killed off particles and start generating the grass from there. Afterwards, I'm going to start shaping up the grass using this set position line. And next, what I do is that I'm going to add a randomly procedurated noise onto the grass using the update loop that the particle has, called a particle strip. So over here, what it does is it's going to take in some directional vector of the wind, and it's going to look at the noise value, this randomly generated noise, and it's going to check how much the particle needs to sway at a given particle inside the strip, which you can't see here. So over here is the progress. So this progress it starts from the base of the grass all the way to the top. So the higher the grass is, the higher the progress. So what I do here is that if the grass base is lower, then it won't move that much compared to a higher grass progress. So afterwards I plug that in to make sure that it then be able to sway side by side because of the noise. Afterwards, the next thing is that there'll be a collide with sphere behavior that Unity VFX sphere VFX graph provides. So over here I connect it to the player. So in the inspector of the VFX graph, you can see here that I can able to connect the properties of the sphere collider into the properties here, so that it's able to take real-time information and put it inside here, so it only calculates the effects of the grass patch after it collides with the sphere. So over here is how I render the grass. So over here is the normal bending. So as you can see here, it's a bit 3D like, but if I were to have no normal bending, it looks more 2D. So that's how I do the normal bending of the grass. The other one is the size. So as you can see here, the size of the grass decreases as it goes on the top. So this is using the progress. So as it goes on the top. You can see the Bezier curve where it goes from fatter to thinner as it goes up the height. Next is the color. I interpolate between the two shades of green from darker to lighter color. So as you can see here, as the grass height increases, it becomes more lighter. So finally, how does the grass perform in the game? I decided to test my grass patch that I made using a bunch of different sizes. So as you can see here from the table below, to show how performant the grass patch is, you can see how that even though it renders about 1.3 billion particles, it performed very well at about 120 to 130 FPS. However, when it started having a lot of issues when it started reaching about 19 million particles, or about 300,000 strands of grass. I do find these results pretty good because my computer doesn't have a good high-end GPU. So if we were to be able to run at a better GPU, I think it will be able to render more of these particles without that much efforts. So before I pass on to Ryan, I want to introduce some ways you can use particle systems. So one way you can do is you can make highly realistic fog in your particle system. As you can see here from Returnals, where the fog particles have fluid simulation, the fog in the game are able to react to physics like movement and the shooting of bullets, so as to make it more realistic in the game. Another way is to make the destruction of objects feel alive. As you can see here from one of the destructible objects in Returnals, they are able to harness the power of particle system to make individual debris particle to do its own movement. This makes the destruction of debris quite realistic when players shoot it down. So, thank you. Now I'll pass on the time to Ryan.
Thank you, Thom. I will now be covering the case studies portion of our presentation. So the first game we'll be looking at is Ghost of Tsushima, and Ghost of Tsushima is an action adventure game, and you have to fight against these like samurais and enemies in the game. So in the picture you can see this nicely created and sculpted enemy figure. So the challenge of the game is that it's very expensive for the CPU to render many of these NPCs at once. So the game is like overrun by these enemy armies, and it is very expensive for the game to render all these 100,000 polys with all these fancy materials, and compute all the AI animation for these NPCs, especially if like it's like at the start of the game where there's like a horde of enemies. So it'd be very expensive to have all these enemies there. So the solution that they came up with is to use a particle system to spawn the non-interactable NPCs. So since the NPCs are not interacted with and are just kind of there for the visual effect as an aesthetic, they can use lower poly models with simpler idle animations to create the illusion of a horde of enemies there. So although this was like initially made for like the NPCs, they realized that they can use this for other things such as like the smaller animals, such as like frogs. So they animate as the frogs interact with the character, before they despawn, they will like have a jumping animation to like despawn into the wild. So in conclusion, particle system can be useful to not just spawn objects, but even animate them while maintaining a low CPU usage. The next game we're looking at is God of War, and this is also an action adventure game where you have to fight against like monsters and like kill the enemies. So the challenge that this game faces is that after you kill like the enemies in the area, all the enemies' dead bodies will start to pile up, and this will cause issues with increased workload on the GPU and the CPU. And the developers cannot really just despawn the enemies after you kill them, since it's not really in line with the team. So they had to find a way to decrease the workload on the CPU and GPU while having a way that is like in team with the game. So the solution that they created was like to disintegrate the mesh using a particle system, and they were able to do this by emitting particles from the mesh before it disappears. So they've done like a combination of alpha reference testing and particle emission, and as you can see from the video, it gives a very visually appealing disintegration effect with a built-in level of like detail. So this was actually very valuable for like effect artists, so they can use this in many scenarios such as like revealing hidden walls or even magic effects. Yeah. So as you can see here, there's like after he hits the enemy, there'll be like some particles coming out, and when he kills the enemy, they'll slowly disintegrate while emitting the particles. So the last game we'll be looking at is Forza Horizon 5. So this is just an open world racing video game, and the challenge that this game faces is that there are many like destructible props in the game. So like in the picture here, you can see like they can hit the tree and it'll be destroyed. Hit like the small little house, the fences, the chairs, and it's very expensive for the CPU to render all the debris made from these destructible props, since there will be many different kinds of debris made from all these props as well. So the solution they came up with is to use a particle system that is highly customizable and reusable to generate the different types of debris. So they're able to do this by having multiple different parameters that is passed to the particle system. So like impact energy, car velocity, and even like car mass, all these factors into the way the particle is being emitted. So this optimization is crucial for maintaining performance across different platforms, and considering the game's like dynamic and fast-paced nature. So like example, the car hit the prop slowly, the debris intensity will be lower, and like maybe fly by slower. But if the car was to be fast and like was like heavy and hit it hard, right, there will be more debris that comes out, and the debris will fly by faster. So using parameters in our particle system allows more customization and control of the particles in game, and will help us create multiple effects while using minimal resources. So the problem statement that I would like to dive deeper in it would be that Ghost of Tsushima, there are many objects with many detailed animations and materials, and rendering multiple of these objects will cause frames to be low, so like less than 15 FPS, and it will make the game unplayable. So how can we solve this? The solution that I had come up with is to use a particle system where I use the lower poly animated particles, but I'll be using game objects, and there will be many parameters that are being passed through into the particle system, so that it will make the particle system more customizable and reusable for different objects. So why am I using like the game objects? So the pros of this will be that I can use the animator component to make it easier to animate, and there'll be like better details. So they already created all this like rigging and sculpted all these beautiful objects to be in the game. So we'll just be using that, and I can instantiate many of them at once. But the one con of this would be that it's very expensive on the CPU. So creating and destroying the objects over and over again can actually like cause increased workload on the CPU. So how can we make it less expensive? Well, I can introduce object pooling. So instead of creating and destroying all these objects, I'll be taking the objects from a pool so that I can keep reusing the same objects over and over again. So initially there will be a pool of objects which I create at the start, and instead of creating new objects, I'll just set the objects to be active into the scene, and whenever I need it, I'll set it as active, and when I no longer need it, I'll set it as false, so that it's no longer active in the scene. And this would actually decrease the workload on the CPU, and make the game more make it more efficient. So the only component we will really need is the animator component, so that our game objects will have animation. We wouldn't need the rigid body or like colliders, since our particle spawner, just like the Ghost of Tsushima, is kind of there for the aesthetic and doesn't really need to be like collided with. So the scripts that we'll be needing will be like 3 different scripts. So the first will be particle script, which will control the lifespan and the movement of the particle. We also have the object pooling script, which will control like the amount of objects to pool at the start and how to use the objects in the pool of objects. And a particle spawner script, which will be like the brains of the operation. So I would like my particle spawner to have all the variables in there, and then from there I'll pass in the variables into the particle script and into the object pooling script, so that everything is being controlled from one script. So this is like a quick preview. So without object pooling, I think I'm spawning about 100. I'm trying to spawn like 1,000,000 of these with like a lifespan of like a minute, and as you can see, it's about 50 FPS. So it's not that bad, but it's still not that great. And with object pooling and the same amount of objects being spawned, I have like almost like tripled or more than tripled the FPS. Yeah. So now I will show you guys my implementation. Okay, so for the implementation, what I have in my scene right now is my particle spawner, which is bound by the scale. So depending on how big this is, that's like how big like the spawning area is from the particle. So the variables I have is the prefab of the particle, the lifespan, which is how long the particle will be alive for, number of particles, so I have it set to quite a big number now. Interval is the interval at which the particles will spawn at, and I have random spawn position check. So in this box that I have here, the particles will spawn like randomly inside this box. And then for object pooling, I'll be pulling 250 objects, and this just ons the object pooling or enables it. And then move to target just makes it so that having this on will make it walk forward in the direction of the spawner. So I want to hit play, and as you can see, it will start spawning the enemies out, and it starts spawning the enemies out. And as you can see, the FPS is about like 200, average like 200 FPS for this many objects. So as you can see, the objects will like run, and after a certain point they will either despawn, or if needed to, they'll be used again here before they despawn. So they'll be used here again because of the object pooling that I have here. Yeah. So how does that work? So our main three scripts will be the object pooling, particle, and the particle system itself. So starting with the particle, over here we have we have like 4 variables. So like we have lifespan, move speed, move forward check. So if this was like not true, the objects will just stay still. And we have float time. So this time is like it's just to check if the time goes over the lifespan that is set, then they will be like set to false. Yeah. So over here we have a lot of getter setters, since I felt that the particle system should be the one that controls all the variables. So using getter setters here, I was able to from my particle system and like put the variables into the particle itself. Yeah, so to move the particle, I just have I get the forward of the particle, and then I just transform the position, and then I add the vector times the move speed, and then times the time fixed delta time. Yeah. So this will make it move forward based on the move speed. Next I have the object pool. So over here I have the amount to pool, which is like the amount of objects to create at the start of the game in the object pool. So here, so to do that, I just have I have a for loop here, right, with I less than amount to pool, and then every time it will instantiate the object to pool, and then I have it to set the parent to the object pool, here, so that it won't get like very messy as like everything like just comes out here. Everything will be like under this one object pool, and I set it to false. So at the start everything will be false, and then only when the spawner spawns it out, then it will be set to active. And then for the object pool, I use a queue. So I queue up all these objects so that whenever I want to use one, right, I'll dequeue it, and then I will re-queue it into the thing. So as you can see from my spawn from object pool method, I take in a vector tree position and a rotation, and I object pool.dequeue to get the first object in the queue, and then that will be the object that I'll be spawning. So if this object is already in the hierarchy, right, I'll actually set it to false first, and then I'll reset it to true. This is because my particle has an enable for time equals 0. So if I don't set it to false and then back to true, right, and just set it to and I don't set it to false, it will make it so that the time will keep counting and will not reset to 0. Yeah. So I set it active, and then I set the position and rotation of the particle to spawn, and then I enqueue this back to the bottom of the queue, so that after the entire queue is like finished already, this will be like the last one to spawn, right? So like this will queue up again, so I can use it again in the object pool. Yeah, so here I also have a lot of getter setters, as I also want to use the particle system as the main variable setter. Yeah, so that's about it for the object pool. So lastly, we have the particle system. So for the particle system, I take in the prefab, which is what I want to spawn, which is the particle, the lifespan of the particle. So I also have number of particles, so it's like the amount of particles I want to spawn. Interval, like I said, is the interval at which the particles will spawn. And then having random spawn position set. So if I so first, if I have object pool check, right, so having object pool check would allow me to use the object pool. So if I don't have it checked, I will just spawn like 100,000 of these objects. Yeah. So let's say we have the object pool check. So we're using object pool. So depending on the number of particles we have set, we will first check if it's random spawn position is true. So if random spawn position is true, we will get the random spawn position, and then get random spawn position, we will get the particle from the object pool. So object pool dot spawn from object pool. We put in the random position and the rotation of the particle system, and then we will set the particle variable of the particle. Yeah. So we'll set the particle. So get random position. Basically, we just get random position from the range of the bounds of the box. So the x and the this is z scale, and then we return that random position. For setting variables, we will set the particle variable. So we take in the particle game object for that particle, and then we take the particle script, or the particle class, I mean, and then we set the lifespan, move speed and move forward check of the particle here. So this is so that like my particle system is like the one like controlling everything, just like the Unity's like particle system, where it's just that like one component. Yeah. I also have a particle system editor, but this is like not really that relevant, but it helps me puts all my thing neatly, so that it's easier to use and see. Yeah. So that's all from my implementation. Thank you.